today in my lecture on chemical thermodynamics, I shall try to explain or rather search the different criteria for spontaneity and equilibrium of a process. In the second law, any statement which provides the conditions for feasibility, direction and extent of a process, that statement can be taken as the second law of thermodynamics. So today I shall search different thermodynamic properties of the system by which we can state whether the process occurring in that system becomes feasible and when it attains equilibrium. Let us start with suppose this is the initial state, and this is the final state. This is the initial state, this is the final state. And here the entropy, let S1, and here the entropy S2. If the system proceeds from the initial state to final state in a reversible process, if the process is reversible process means this process will consist of an infinite number of steps, and in each step the system attains equilibrium. So this is why the reversible process we can call the equilibrium process. And suppose in this process, in this reversible process, for the system to pass from a initial state to final state, say D cross and Q, a reversible heat change occurs. Very small amount of heat change occurs. This amount of heat have been absorbed from the surroundings at a constant temperature. So this process is reversible as well as isothermal. And according to the Clausius, this entropy change of the system between the two definite states is equal to D cross Q reversible by T. T the temperature at which this heat change occurs. And you know it is the D means S is perfectly differential, and this is why its change is fixed between the two states, and D cross Q reversible or heat change is not a perfectly differential quantity, and so instead of D here I write D cross, and it is the temperature at which the heat change occurs. If the process occurs in this irreversible path, irreversible process is a sudden process. In the case of irreversible process, the system changes from its initial state to final state spontaneously. As we know from the second law of thermodynamics, any spontaneous process or the natural process is thermodynamically irreversible, and the process always tend to attain equilibrium. So in this case, suppose this is the irreversible process. Irreversible process. It is a reversible process. And in this case, say heat change Q d cos Q irreversible. Q irreversible heat change occurs at this temperature T, and this process is spontaneous process. But we know this d cos Q reversible is greater than d cos Q irreversible. It can be shown in first law of thermodynamics. Actually, d cos Q reversible plus W reversible equal to du, and d cos Q irreversible plus W irreversible, this is also equal to dw. So du. So du, this is the change internally. The change internally between the two fixed states of the system is always same. So these two are same. So these two are also same. But we know in case of reversible process, it is the work done on the system, and for this reversible process, and it is also the isothermal process. In this case, the W reversible is minimum. It is the minimum. Then this one, this is greater. So since this is the minimum, so this one is greater than this one, and this one is less than this one. So this one is greater than this one. So this it could be written in this fashion. So from this conclusions, I can draw that ds entropic change, which is the same whether the process is reversible or irreversible. So this one actually greater than d cos Q irreversible by T. So this one sometimes is called Clausius inequality. It is actually called Clausius inequality. Clausius inequality. So if we jointly consider these two processes, reversible and irreversible, then we can write this ds greater than equal to d cross Q and divided by T. Whenever this process is irreversible, inequality sign will be appropriate, and when this process is reversible, then equality sign will be there. For any process, if you consider, then spontaneous process means thermodynamically irreversible, and that will ultimately, its ultimate goal to reach this equilibrium, and this reversible process is equilibrium process. So if we replace this, so T ds greater than equal to d cross Q, and instead of d cross, we can write d cross Q plus W work done on the system, it is equal to d. If W is mechanical work only, or mechanical work or pressure volume work only, then it could be written as minus PdV. So instead of writing this one, we can write this d cos Q equal to du plus p dv. P. So this equation, this instead of write this one, we can write this t ds greater than equal to du plus p. Or you can say this t ds minus du minus pdv greater than equal to 0. So this is the starting equation to search the different criteria for spontaneity of a process. Now let us consider the criteria. Criterion 1. First criterion. Whenever at a constant u and v and at a constant v, we can write du fixed, u is fixed, du 0, dv also 0. So in this case t ds greater than equal to 0. Or we can write ds and u v fixed greater than equal to 0. For a macroscopic change, change of the state of the system, we can write del s u v is greater than equal to 0. So this is the first criteria. This is the first condition, first criterion in terms of this entropy. So I can write here the first criterion 1. This del s u v greater than equal to 0. What this condition is giving the meaning to us. Actually, whenever the process occurs spontaneously, means irreversible process, then the entropy, entropy will increase. Means here the entropy is, and whenever the process occurs spontaneously, entropy will increase, and delta S equal to positive or greater than 0. So whenever entropy increases and then entropy attains maximum value when the spontaneous process attains equilibrium. So here this entropy is increasing for the process to occur spontaneously, or I can say this del S positive or greater than 0. When it attains equilibrium, when this process will attain equilibrium, then S del S, here uv is there, equal to 0, and means the process attains equilibrium. You can see for this process where this U and V are fixed. You already I have shown this D cross Q equal to du plus PdV. When V is constant and U constant, these two terms equal to 0, so this is equal to 0. It means that no heat exchange occurs between the system to surrounding. So as no heat exchange occurs between the system or surrounding, this is only possible in a system which is the isolated. So this one is valid for isolated system. Isolated system. So whenever this system is not isolated, in that case, not only the entropy change of the system is not sufficient to put the criteria for the spontaneity of a process which is occurring within the system. So in that case, we shall have to consider this del S system plus del S surrounding equal to del S universe, and this one greater than equal to 0. So whenever the process is occurring within the system, we shall have to calculate the entropy change of this surrounding with which the system is interacting. So this one is not easy to calculate. So though the process is general, this process is general. Actually, del S universe greater than equal to 0, and it is valid for not only for this isolated system but valid for other systems also. So this is general, but due to this handicap to calculate this entropy change of the surrounding, this process is not a practical one. So let us consider the second criterion. Let us consider this second criterion. Whenever, say, suppose at a constant entropy and at a constant V, entropy is constant, ds equal to 0, volume is constant, dv equal to 0, so these two terms equal to 0. So minus du greater than equal to 0, or I can say this du at constant entropy and volume less than equal to 0. And for macroscopic change, or macroscopic change of the states of the system, you can write del U S V less than equal to 0. Well, this is another statement. This statement 2. Del U S V less than equal to 0. So this is also a nice one, but one problem is that whenever the process occurs spontaneously, this its entropy under these conditions, internal energy will decrease, and internal energy will decrease and attains U minimum. When this internal energy attains minimum, this system, the process will attain equilibrium. When the U is minimum, the process will stop. So here, for spontaneous process, so long the process occurs spontaneously, spontaneously, this U is a decreasing. U is a decreasing and del U less than G. Here at equilibrium, when the process is at equilibrium, del S equal to del U equal to G. So for any conservative mechanical system, that system will try to attain this minimum internal energy, and in that case this system becomes stable. And now, but this criteria faces some difficulty. Actually, this entropy, constant entropy, is very difficult to keep in a system whenever the process is occurring. Suppose if we consider, say, any reaction, say nitrogen gas plus 3 hydrogen gas, some chemical process I am referring here, this twice ammonia gas. As this reaction process in the system, the entropy is decreasing as the number of molecules are decreasing due to this reaction. So entropy is also decreasing, randomness decreasing. So entropy very difficult to keep a constant for the system where the process is occurring. So this criteria is not so practical one, not so useful. Whenever we keep now criterion 3 at constant entropy and constant pressure. In this case, this one could be shown easily that del H at constant S and P less than equal to 0. It is the similar criteria for this one, and this third one del H and S and P less than equal to 0. And this could also be reduced from this one. As if here you can write at constant S and constant P, we can write this du plus pdv minus tds is less than equal to 0 here. But whenever this S is fixed, means this becomes 0, so P constant, so U plus PV at constant entropy and pressure is less than equal to 0, and sum of the two equal to 8 enthalpy. This condition is also very nice to look, but not a practical one. Here also entropy has to be kept a constant, which is not so possible. Now I am coming to this fourth criteria. At a constant temperature and constant volume. In this case, this one I can write this du plus p dv minus t ds less than equal to 0. We can write v constant means this becomes equal to 0, so du minus t constant ts and here t and v less than 0. But we know that u minus t is equal to A, which is the work function or Helmholtz free energy. So this dA at constant temperature and volume less than equal to 0, and for microscopic change this delta U delta A T V less than equal to 0. So this criteria is better than all these three. Then four criteria, this del A and T and V less than G. So whenever suppose this is the A, whenever the process occurring in this system, the system's work function will decrease, and here this A attains a minimum, and this is here it is the A is decreasing. A is decreasing whenever the process occurring spontaneously, and for spontaneous process, and del A is less than 0 or negative. Here at equilibrium, the equilibrium at del A at constant temperature volume, equal to 0. So this is a better. This one is the better criteria than this above three. And del A at constant temperature pressure, del A could be written as del U minus T del S. So whenever del U, it is the heat of reaction at constant volume, or the internal energy of this reaction is negative, means exothermic reaction. Whenever the reaction or the exothermic process, whenever the process is exothermic, this one is the favorable conditions, and del S, if del S is positive, means randomness increases, and these two randomness increases due to this process. If then this one is negative, this one is also, this term also negative, delta A is negative, so this process, these two conditions will favor for this process to occur spontaneously. So next the fifth one, then the criterion fifth constant temperature and constant pressure. This is the best criteria. This is the best criterion for the spontaneity, as most of the reactions occurs at constant temperature pressure. Not only the reactions, chemical reactions, but also or any process, but also in galvanic cells, the cell reaction that produces the electricity, that cell reactions occurs at constant temperature pressure, at room temperature, room pressure, even in our human body. So say various physico-chemical processes are occurring at atmospheric pressure, and also the temperature is the body temperature 98.4 degree Fahrenheit. So this criteria is a very useful one. This could be done in this way: du plus pdv and minus pds less than equal to 0. But p is constant, t is constant, so I can write u plus pv minus ts and constant temperature and constant pressure less than equal to 0. Or I can write d, these two, H enthalpy minus Ts at constant temperature and pressure less than equal to 0, and this H minus Ts, you know, H minus Ts equal to G, which is called, gives free energy, and gives free energy has the largest contribution in this chemistry. So we can write, or D and G, temperature, pressure less than equal to 0. For macroscopic change, for macroscopic change of the state of for the system, we can write del G, T and P less than equal to 0. So this is the fifth criteria, and I think this one is the best one. G, T and V less than equal to 0. So altogether we are having this 5 criterion. So next question comes up. This at constant temperature pressure, the criteria becomes del G temperature pressure less than equal to 2. As the process occurs spontaneously in a system, this is the free energy change of the system, and the system have been kept at constant temperature and constant pressure. So long this reaction G will decrease. The G will decrease for spontaneous process. For spontaneous process, and G is decreasing, and del G is less than 0. Here G is minimum, and the equilibrium process becomes equilibrium, and del G equal to 0 at constant temperature pressure already implied. For simplicity's sake, we can remove this constancy of temperature pressure, and so if we calculate this delta G of a process, then we can decide whether the process will occur or not spontaneously. So this calculation of delta G at constant temperature pressure is omitted. Say for a process, how can I calculate this one? So this del G equal to del H minus T del S. So for a process, if we calculate this delta H could be calculated for any process. Say suppose for a reaction, so this one is better way to be calculated by using this Born energy. In my lecture in thermochemistry, I have shown how this enthalpy of a reaction could be calculated by the use of this Born energies, provided the structure of these reactants or products should be known. And not only that, it could be experimentally determined by means of calorimetry or by means of Ventov reaction isobar, or by means of the EMF of the cell, for the reaction by which this cell is working, and delta S also obtained from this EMF study. But delta S suppose S2 minus S1, S2 minus S1, these are the absolute values, and absolute values could be determined by the could be determined by graphical method by using this third law of thermodynamics. So this could be calculated. This one will calculate if the reaction, if you do not know whether the reaction proceeds or not, whether this reaction will occur or not, still then its del H and del S could be calculated theoretically. This one from Born energy, and this one from this third law of thermodynamics. So now we can consider the different favorable conditions, or I can say the critical discussion, critical comments for which this delta G will be negative for this spontaneous process. One comment, say for this process delta H is negative, means exothermic reaction, and this del S is also positive. Positive means randomness of the system increases due to this process, due to the process. So this one is the negative. This term is also negative. Both the conditions are favorable for the process to occur spontaneously, and delta G becomes negative. In this case, delta G always negative. Negative always. One example I can show here. This hydrogen peroxide liquid and giving this hydrogen water decomposition liquid plus half oxygen gas. So here randomness increases as this gas is being produced, and this one bond rearrangement will show that this delta it is an exothermic process. Now the second comment, comment number 2. Delta is negative, but this one is also negative. Means randomness of the system decreases. Of the system decreases due to the process. So in this case, this one is favorable. But this term is not favorable. Delta S always for the condition of spontaneity, the entropy or randomness will increase. But in this case, this entropy is decreasing. Delta S is negative. Delta S negative means this one is positive and this one is negative. If delta G has to be negative value, then this one magnitude of del H must be greater than magnitude of T del S. Or I can say this del H by del S modulus is greater than T. Means this reaction occurs at low temperature. For these type of reactions, more favorably occurs at low temperature. At low temperature, this one is unfavorable conditions. This term becomes minimized at low T. So this is favorable at low T. One example I can show here. Say ammonia gas plus HCl gas and giving this ammonium chloride solid. So this is very important. This one is very important reactions to identify the gas, whether it is ammonia or not. Issuing gas, if you keep a rod dipped in a HCl solutions and put in the at this issuing gas, this white fumes of ammonium chloride will be formed. So in this case, you can see as the bond is formed, so heat is liberated. But here two molecules are uniting to give one molecule. So randomness is decreasing. So now we are giving this criterion 3. Criterion 3. In this case, suppose del H equal to positive means endothermic reaction. Endothermic reactions, heat is to be applied to make this reaction process, and del S is negative. Del S is positive. Del S is positive. Del S is positive means randomness actually increasing due to this process. So here this term is not favorable, but this term is favorable. This term is negative, and this negative term, whenever overcome the positive value of delta H, delta G becomes negative. So for this for making this delta G negative, actually this T del S must be greater than modulus del H, or T we can say is modulus of del H by modulus of del H. Means this sort of reactions under this criteria will occur spontaneously at high temperature. So any case of any thermal dissociation, say suppose phosphorus pentachloride gas and giving you phosphorus trichloride gas plus HCl plus chlorine Cl2 gas. Yes. And this reaction is possible at a high. This reaction is possible at high. So this now next we shall the fourth critical comments. It is the critical comments. Comment. Comments 4. Now the last one. Suppose delta H is positive and this one is negative. Means randomness decreases. In this case, you can see both the terms are not favorable. This one is the positive term, so this term also, second term also positive term, so delta G always positive. So delta G is always positive, and this sort of reactions will never occur spontaneously. Reverse reaction may occur spontaneously. One example I can show: this nitrogen gas plus twice oxygen gas and giving this twice NO2 gas. In this case, the degree of randomness is decreasing as entropy is negative, and this process is also the endothermic reactions. This delta H and delta S could be calculated for these reactions not by experimental data but by this one from this bond energy and this one by using this third law. So this one, the critical comments based on the delta A, based on the fifth criterion, and this one is the best one. And now I can put some example. Some examples. One you can say, suppose A and G plus A, this is G, and giving this A to G. So this is actually dimensional process, and suppose let us take delta H equal to 0 for this process, and you have to judge whether this process will occur or not. So this del G equal to here del G equal to del H minus T del S. Here del H equal to 0 and minus T. For this reaction, this randomness decreases. Randomness decreases as two molecules uniting to give you one molecule. So this one is also, and to be changed negative. So this one is a positive. Positive means, it means that this reaction is not possible if delta H is 0. However, if delta H is negative exothermic reactions, and this one may overcome this handicap, then it may be possible spontaneously. So example number 2. Example number 2. For this case, suppose 1 mole water liquid, and giving this 1 mole water vapor, and it is the process of vaporation process. This is the process of vaporation, and I like to see this vaporation process boiling occurs at constant temperature pressure. Suppose this pressure P is taken at 1 atmosphere. Now I am to see at what temperature this process or the vaporation process becomes spontaneous. In this case, you just see, I can put here this value del G. For the process to occur spontaneously, this del G less than 0. And at equilibrium it is equal to 0. So del G, instead of del G we can write del H minus T del S less than equal to 0. Or we can write this T is greater than modulus of del H and divided by modulus of del S. But at constant temperature, constant pressure, at 1 atmosphere pressure, this del H equal to for 1 mole 18 into 540 calorie more inverse. This is the latent heat of evaporation for 1 mole of this liquid, and this one. For this case of this process, it is a 26 calorie Kelvin inverse and mole inverse. So this gives you the 373 Kelvin or greater than 100 degree centigrade. 100 degree centigrade. So this infers that whenever the pressure is kept at 1 atmosphere, the evaporation of water becomes spontaneous at a temperature more than 100 degrees. Whenever the temperature becomes more than 100 degrees centigrade, this process occurs spontaneously. But whenever the temperature equal to 100 degrees centigrade at 1 atmosphere pressure, this too remains at equilibrium. This means the evaporation stops. And then another this third examples. Third examples. This is also very famous example. Say carbon. This carbon solid plus steam, red hot carbon. It is red hot carbon. It is the steam means gaseous state, and this is carbon monoxide gas and plus a hydrogen gas. These two are collectively known as the water gas, and this water gas is very helpful to in the manufacture of this ammonia. This is the raw material for this manufacture of ammonia. So in this case, say at 1 atmosphere, suppose del H for this reaction is 31,400 calorie, and del S equal to 32 calorie per Kelvin inverse at 1 atmosphere pressure. So if now find find the feasibility of this process, feasibility of the reaction at 100 degree centigrade and at 1000 degree centigrade. We have to see at 100 degrees centigrade, this del G, we have to calculate this delta G from these values. So it will be 31,400 calorie and minus 373 Kelvin, as it is the 100 degrees centigrade, into 32 Kelvin inverse, and this one gives, and this one actually the plus 19,464, and this one is a positive value, means this reaction is this one calorie and this calorie, and this at this 100 degrees centigrade, this reaction is not possible, not feasible, not occurring spontaneously. But if we consider at 1000 degrees centigrade, this will be equal to 31,400 calorie minus, in this case, temperature 1273 Kelvin into 22 Kelvin inverse, and this one actually minus. This one gives you this minus 9,336, minus 9,336 calorie. So this is negative. So this term is negative, means this reaction will be feasible at 1000 degrees centigrade and not at 100 degrees centigrade. So this temperature actually controls whether this process will occur, whether this reaction will occur or not. So one thing I like to note here, that in 100 degrees centigrade and 1000 degrees centigrade, in both the cases, delta H and delta S, the same values are inserted. Actually, this is due to the fact that delta H and delta S does not change the temperature so significantly, but delta G changes with the temperature most dramatically. As you see, whenever the temperature is increased, this positive value 19,464 calorie turns over minus 9,336 calories. So much drastic change occurs whenever the temperature is increased. So delta G changes very significantly with this temperature. So what we do actually at our convenient temperature, at our own convenient temperature, we determine this delta H and delta S for this for the reaction, and these two values we compute for approximate determination, approximate calculations of this delta G at this temperature, and we see at what temperature this process will be feasible. Spontaneous process means this process occurs by its own accord. But so far, I did not say anything, did not tell anything about this rate of these reactions. Thermodynamics remains silent about this rate of this process. The process will be feasible. Process will be feasible at 1000 degrees centigrade. This process is feasible at 1000 degrees centigrade, but the rate of this process, the thermodynamics cannot tell. It is the subject matter of this chemical kinetics. So thank you all. Today I shall discuss. Today I have discussed fully the criteria of spontaneity of a process very elaborately with 3 examples, and in my next class I shall discuss the Joule-Thomson effect. It is a very important effect to cool down of a gas, and this is very urgently required for liquefaction of a gas. So thank you all.